Thank you. It's such a great honor to be here today and to have asked to have been a speaker at this session. I wouldn't be here today were it not for my parents, who instilled in me a love of science, even at a very young age. Some of my earliest memories are of my dad reading to me from a book about the hot volcanic young Earth. It was a book called The Earth for Sam, and it was one of my favorite books. My parents were endlessly supportive of me in all of my varied pursuits, from science fairs in grade school. I think it was the hairdo that really did it. To years of ballet lessons as I pursued the dream of becoming a ballet dancer. Ultimately, I came back to science, and it was at Duke University that I was really inspired by two amazing professors, John Kalina in astrophysics and Horst Meyer in advanced physics lab, and they really inspired me to pursue graduate studies. My thesis advisor, Larry Esposito, started me on models of planetary ring dynamics, and then was very supportive when I decided halfway through my thesis that I wanted to change topics and work on the origin of the moon instead. I'm forever grateful to him for that because it's been a topic that I've been interested in ever since. Soon after I got my PhD, I joined what was then a small remote office dedicated to planetary science of the Southwest Research Institute. Southwest is a nonprofit, private institute based in Texas. The planetary group in Boulder has grown greatly ever since, and it's a wonderful and supportive environment to conduct planetary research. It was at Southwest that I met and started working with Bill Ward, who has been my closest scientific collaborator now for the past 15 years. And finally, and most importantly, I'd like to acknowledge the love and support of my family, my husband Rick of the last 20 years, and our children Natalie and Asher. So I'm going to talk about the formation of the primary moons in our solar system. These are a highly varied group of objects, and we think their origins are tied directly to the origins of the planets. I'm going to start with a plot showing very basic properties of the satellite systems. So I'm plotting the mass in the satellite system, ratio to the planet's mass, as a function of the radial scale of the satellite system shown in planetary radii. And on this first plot are the satellite systems around the solid planets and the dwarf planets that we now know exist in the outer solar system beyond Pluto. These systems show a wide diversity on this plot, ranging from tiny satellites of Mars all the way up to the relatively quite large satellite of Pluto. In stark contrast are the satellite systems around the gas giant planets. They are closely clustered on this plot. This is because they each contain a nearly identical fraction of their central planet's mass, about 10 to the minus 4. And this similarity is very surprising because we think that each of these planets would have grown by quite different circumstances. So the fact that they share this property we think is a real clue to their origin. So I'm going to talk about two different mechanisms for forming satellites that we think may be able to explain these two very different distributions. In the cases of the satellites around the solid planets, we think they may have formed from giant collisions. And for the satellites of the gas planets, we think they formed within gaseous disk around those planets as the planets formed. So the idea that an impact could produce a satellite was first really developed for the origin of our moon. The idea is that the Earth was struck by another planet-sized object as it finished its formation. The giant impact theory, as it's called, is favored because it does a good job of explaining most of the basic properties of the Earth-Moon system. For example, the moon raises tides on the... Okay, I'll put this down while I'm talking. The moon raises tides on the Earth, and the interaction of the moon with these tides causes the moon's orbit to expand over time and the Earth's rotation to slow. From this, we know that when the moon first formed, it was close to the Earth, and the Earth was rotating much more rapidly, with only about a 5-hour day. So an off-center collision by a large planet is a natural way to explain how the Earth got this fast initial rotation. In addition, we know from the moon's bulk density, it's strongly depleted in iron compared to the Earth. And as I'll show you, a giant impact can also explain this. And finally, we think these large collisions were common during the final stages of assembly of the inner solid planets in our solar system. So to model these types of events, we use 3 three-dimensional numerical simulations. The ones I'll show you represent the colliding bodies by a multitude of particles, typically 100,000 or so. And you track the individual evolution of each particle as it evolves due to gravity and pressure forces. And an input equation of state then tells you how each particle's material responds thermodynamically to the impact, whether it melts, vaporizes, and what its temperature is. So I'll show you some animations of a potential moon-forming impact. Here the color is scaling with temperature. So 2000 K is represented in blue, that's molten silicate, whereas the red particles that you'll see at low pressure are vaporized silicate. So here the Earth, the lower left, is being struck by a Mars-sized impactor on the upper right. So the initial impact, pause it here if I can, destroys the impacting object. After a few hours, in this case, the inner portions of the impactor actually coalesce into a clump that re-impacts the Earth. There's another large clump out here that you'll see makes a very close pass by the Earth here. And as it gets very close to the Earth, Earth's tides strip it apart, and this material provides most of the mass in what is a disk around the Earth after this simulated 24-hour period. So we have a rapidly rotating Earth surrounded by a disk with enough mass to later accumulate into our moon. So this is the same impact with a different color scheme. Here the color corresponds to material type. And you can see that we're assuming that both objects initially have large Earth-like iron cores. Because of the geometry of the impact, the iron core of the impactor collides more directly with the Earth. And as that inner clump of impactor material collides with the Earth, it contains most of the impactor's core, so that as it collides with the Earth, most of the iron is removed from the disk. So that in the end, the disk has only a few percent iron by mass, and that's consistent with the amount of iron that we believe is in the moon. So this is the last animation of that same collision. This one is in 3D, and in particular, you'll see that the most strongly heated material at the initial impact site, those are the red particles, will wrap itself around the planet and form a silicate vapor atmosphere around the Earth. Okay, there's the initial collision. Here are these vaporized particles wrapping around the Earth. This is the iron core of the impactor coming in for that secondary impact. As the simulation progresses, our viewing point is moving. And so we're now going to move into the plane of the disk. So we're looking at the planet on edge. You can tell it's very oblate. That's because it's rotating so rapidly with a day of only about 5 hours in this case. And now we're going to be looking from underneath the planet. There's that outer clump that gets stripped apart. So this collision has been optimized to produce a disk capable of producing our moon. But if you consider different types of impacts, you can produce very different types of disk. And in some cases, you can even form an intact satellite directly from the impact itself. This is a type of collision that can produce a Pluto-Charon-like pair, where the satellite is very massive compared to the Earth. So using lots of these simulations, one can find that a wide range of satellite system properties can likely result from these impacts. Each of these points are results from one of the impact simulations like the ones I've shown. So in general, we think we can explain the diversity of solid planet systems from these giant impacts. So let me turn now to the origin of the satellites of the gas giant planets. I'm going to focus on the satellite systems of Jupiter and Saturn. Around Jupiter, of course, we have the 4 famous Galilean moons. They're each similar in mass to our moon. If you combine their mass and ratio to the mass of Jupiter, the system contains a mass ratio of 2 times 10 to the negative 4. At Saturn, we just have one large satellite, Titan. And Titan contains more than 95% of the mass in the satellite system. Saturn also has a massive, essentially pure ice ring system that distinguishes it. But despite the fact that this system looks very different from the system at Jupiter, if you take the mass of all the satellites and ratio it to the planet, you see a nearly identical mass ratio. So both Jupiter and Saturn are mostly hydrogen and helium gas by mass. So that tells us that they must have formed when the sun had its hydrogen and helium-rich gas disk, which we think it would have had for the first few million years of its life. This is a hydrodynamical simulation of a gas giant planet growing from such a disk, looking down from above. The brightness here scales with the gas density. If we zoom into the region around the planet, you can see that the inflowing gas, and the arrows here indicate the flow streamlines, has too much angular momentum to fall directly to the planet, and so it instead forms this circumplanetary disk. So as the planet grows, we think it had a hydrogen and helium-rich disk around it. Now, the inflowing gas would have carried with it any small entrained ice and rock particles. And as those particles went into orbit around the planet and collided with each other, they could grow into satellites. So there's an important process that would affect a satellite growing in a gas disk, and it's called type 1 migration. The satellite's gravity induces the formation of spiral density waves in the gas disk, and those are these waves you're seeing here. The back gravitational reaction of those waves on the satellite orbit caused the satellite's orbit to spiral inward and eventually to hit the planet if the migration continues. The rate of this migration is proportional to the mass of the satellite. So the bigger the satellite gets, the faster its orbit decays, and it's also proportional to the gas density, so that as the gas went away, when the solar nebula dissipated, this process would have ended. So I'm going to show you a simulation of satellites growing in such a disk around a giant planet. The simulated satellites are shown by the black circles here. The horizontal line through each one is proportional to the orbital ellipticity of the satellite's orbit. The red stars are the Galilean satellites. As the satellites grow, you'll see them move up this plot. This is showing the satellite mass. And as they migrate inward, you'll see them move to the left until they finally are near the planet and removed from the simulation. So the inflow delivers mass to the disk. Satellites grow. But they only grow until they reach a critical mass at which the time scale for their growth becomes comparable to their time scale to be lost due to this type 1 migration. At that point, they can't grow much more before they decay inward. Ongoing inflow to the disk adds more material, and another generation of satellites grows until it reaches that critical mass and then is lost. The plot on the right shows the total satellite system mass in this simulation as a function of time. It grows initially as the inflow supplies material to the disk, and then it decreases in discrete steps as we lose the big satellites to type 1 migration. And essentially, type 1 migration acts like a negative feedback on the mass that can be held in this satellite system. So it causes the mass to oscillate around a relatively fixed value, which for common disk parameters is comparable to the 2 × 10⁻⁴ mass ratio we see around Jupiter and Saturn. So what we're really interested in is the last generation of satellites that formed in such a process, because those would be the ones that we survive and probably the ones we see today. So in this animation, we're considering an exponentially decaying inflow with time. And in this case, as the gas inflow to the planet ends and the gas disk around the planet dissipates, the type 1 migration process is slowly turned off and the final satellite orbits can stabilize. So this is an example of a system that after a few million years results in 4 large satellites that are similar in mass and orbital spacings to Jupiter's Galilean satellites. But depending on when the gas inflow to the planet ends, compared to these cycles of satellite formation and loss, you can get very different types of final satellite systems. This simulation shows the same basic conditions. And you can see here initially, there's 4 large inner satellites that are just about as big as Titan. That's represented by this star here. And 1 large outer satellite here. But in this case, the 4 inner large satellites are lost just as gas inflow to the planet ends. So the final system in this case just has 1 large satellite, a Titan-like analog. This is interesting because it can not only explain why a planet might end up with only 1 large satellite, even though it had a broad disk around it, but it also offers a potential means to produce the rings of Saturn. If a very large satellite, say the size of Titan, which is comparable in size in mass to our moon, as such a large satellite forms, it seems probable that its ice would have been heated to the point of melting. And once that happens, any rock that's in the satellite will rapidly coalesce into a rocky core in the center. As a large satellite that has a rocky core and an icy mantle spirals very close to the planet's tides will tend to strip off the icy outer layers of the satellite and form a massive icy ring, while the rocky core, by virtue of its much higher density, can maintain its stability until it ultimately hits the planet. So in this way, the same process that could be responsible for why Saturn doesn't have an inner large satellite currently may also be responsible for the creation of its massive icy ring system. So to conclude, the process of giant impacts can produce a very broad diversity of satellite systems, similar to those we see around the solid planets and dwarf planets. And it's possible that the formation of satellites in gaseous disk around growing gas giant planets will naturally select for a common satellite system mass ratio similar to that seen in our solar system. And this may actually be a testable prediction in the future as we become able to observe or at least place limits on the properties of satellites around extrasolar giant planets. Thank you.